Good afternoon, everyone. I am Devyani from IETE-ISF, and I welcome you all to the speaker session of VIT's biggest hackathon, AccessDenied' 2021. We hope you have had a great learning experience. The good thing is that learning experience never stops, and hence we have organized multiple speaker sessions for your advantage. The topic of today's session is electronics product development. The session will be taken by our associate sponsor, Qmax Systems, who has also provided us with a problem statement. To enlighten us on the topic, we have with us Mr. Sarvana Perumal and Mr. Sarvana Bhavan from Qmax Systems. Qmax Systems provides high-quality hardware engineering and PCB design services. It has over 20 years of experience designing complex hardware for the most challenging applications and can provide quick, cost-effective, and suitable solutions for any requirements. At Qmax, they have worked across many domains like aerospace and medical electronics and expertise in application engineering. IETE-ISF takes immense pleasure in welcoming Mr. Sarvana Perumal and Mr. Sarvana Bhavan for their session on electronics product development today. It is our honor to have you with us, sir. Over to you, sir.
Good afternoon, everyone. This is Sarvana from Qmax Systems. We are a product development services company. So we do products from a concept and take it all the way to manufacturing. This includes a lot of different type of electronics for different applications, including aerospace, medical electronics, automotive. Recently, we are doing a lot of projects on electric vehicles. Maybe you can go to the next one.
So I'm Saravana Perumal. Myself and Saravana Bhavan will be taking through you this section. We'll try to make it as interactive as possible. So the whole idea of this section is to give you a full walkthrough of what happens inside when you want to develop an electronic product. Say any electronic product from your mobile phone or a charger or your TV remote, etc. So that's the whole idea of this section is going to be. We'll start from there. About Qmax Systems. Sarvana, you can take it from here.
Okay, so we are around, so we are based out of Chennai right now, and we have offices in US, Canada, and Belgium. We are around 30-member team here, mostly in Chennai, and we're doing products from concept all the way to manufacturing. So maybe you can go to the next one, please. Yeah, our expertise includes different type of electronics, Wi-Fi, for example. Recently, there is a lot of focus on Wi-Fi, wireless, 4G, 5G, and Wi-Fi. The throughput, there's a lot of demand for high data rate. Wi-Fi plays a key role here. So right now, there is a lot of focus on 11AX access points, 11AX devices, end devices. And more also right now, there is a strong drive towards electric vehicle market. So we are developing electric vehicle components like onboard chargers, motor controllers, DC-DC converters, vehicle control units, and battery management system. So there are a lot of electronic components that goes into automotive, and particularly even more in electric vehicles. And we do a lot of complex PCBs, sometimes very high voltage, high current, and sometimes very sensitive, very, very small signal. So if you take an RF input, it's going to be like super small signal. On the other side, if you take a motor drive, it's going to be like very high current and high voltage. These days, the electric vehicles operate at 400 volts DC. And a bigger electric vehicle like electric buses or SUVs, they operate at 800 volts. Okay, so there are high current, high voltage PCBs have to be designed. And apart from that, when there's a very timing critical and fast development cycle, we may need to go with the FPGA based designs. So we work with a lot of FPGA also. And mostly we do like the other products, including medical electronics and wireless communication. Also, as a part of it, today every electronics goes with some sort of software application, microcontroller, firmware development work. Okay. So our expertise includes maybe SP can add some areas on the firmware side.
Correct. Yeah. So on the firmware side, we start with bare metal. Bare metal means just the embedded C, and then RTOS or even Linux-based systems, and also on all the communication protocols. So either it can be a Bluetooth, Wi-Fi, or Ethernet, or even industrial communications. So every stack we have a uh, wide coverage of all the technology landscapes in Qmax. So this will be a very hardcore electronics of firmware development area in Qmax. And also we do communication to the cloud, and the cloud side we have the platform, so that nowadays everything has to go to cloud, right? So we'll take the data up to the cloud and give it to the customers. So in this session we'll pick up different products maybe in the next slides, and just go over the full life cycle, what happens behind the scene. Yeah, let me move on to the next screen. So this is to set the context till now, what we do and what are the things happening here. We'll go into the concept to manufacturing.
So if you see any product, right, so somebody comes with a concept, and so we'll have to take it all the way to production to the customer, right? So take some example, there can be a Wi-Fi access point or a small component that goes into an automotive, like, maybe you can assume something like motor controller for wipers, something like that, right? So we'll have to start from the scratch, from the concept. So there will be a product specification. We can do the product specification architecture, and do the hardware design development, like schematics, PCB design, and PCB fab assembly, and also doing the mechanical design. So mechanical design, that may involve industrial design and mechanical design. On top of it, we'll have to add the firmware development. So when you have a microcontroller, microprocessors, you need to do the firmware development. If it is some new devices getting added, we'll have to do a device driver development. And it goes into a compliance. Typically, most of the products go through FCC, UL, CE type of certification, and then take it to manufacturing. There can be multiple phases in between, just to get an idea. So from concept all the way to manufacturing, that is the background. You can go to the next one.
Yeah.
We will start with the product to explain you what it takes and what are all the steps in a complete hardware product life cycle. Okay. So the hardware product life cycle, meaning it's not just the piece of electronics, right? So it has the firmware that runs into it. There's an enclosure. And there is a whole lot of constraints. So maybe we'll take this as a case study to understand the complete product. We'll go through this step by step and see what it is, right? For example, this is one of the actual product that we did for a customer for an Indian customer. This is a lubrication system for railways. So when the rails when the train go on a curvature, okay, so there can be a friction on the wheels to the rails, okay. So if you see if there is a curvature like this, there will be a lot of friction on the wheels to the rails, okay. So that has to be lubricated. So, but when you see the lubrication over a period of time, it has to be re-lubricated again, and based on certain parameters. For example, a number of wheels, okay, or number of trains. So 10 times, every 10 trains lubricate once, something like that, or every 10,000 wheels lubricate once again, okay, something like that.
The lubrication is between the rails and the wheels, correct, sir?
Yes, correct, exactly. On the sides of the rails, okay.
Okay.
So can you go to the next slide? So
Yeah.
if there is a curvature, then you'll see some some friction on the edges of the wheels, not between the wheels and the rails. There is a side fin. So
Okay.
maybe you can go to the next one. Next, one more. Okay, you can see the lubrication on the side of the rails, okay, not on top of the rail, okay, it's on the sides. If there's a lubrication on this on the rails, it will there will be a lot of slip. Here we want to have some lubrication on the
Side.
sides of the rails, okay. So this will help the train go around the curvature without much of a friction.
So,
Okay.
so that means right now in India, all the turns, does it have lubrication in the railways?
Yes, all the turns, exactly. All the turns in the on the on all the turns will have sort of lubrication. Otherwise, there will be a lot of friction, and the wheels will worn out earlier.
Okay.
So it has to be lubricated. So either they do it. Sometimes they do it manually. So you'll have someone going with a can of oil and lubricate it, or it will be automatically lubricated.
Okay.
So this is for across. This has been installed across India. Not only metro rail, it's also with the regular rail system, with the Indian Railways. Um, so this one, maybe it will be. I mean, it is also deployed in remote locations. Okay, so train goes across India on all different locations, hills, hot place, cold place, rainy place, dry place, forest. So all of these places. So this system has to be installed and with a lubrication tank. So the lubrication tank will be filled once in 2 months or once in 3 months. Then the lubrication is dispensed carefully based on um, the count, the wheel count or the train count. Okay, it depends. And also it communicates to the cloud on how much lubrication is done, what is the lubrication balance, and the other details. We can go to the previous one. Yeah, now to get a understanding, the you need lubrication for the rails which are in remote locations. So this small piece of electronics which will inject lubricant.
Correct. So this is the understanding part of the whole life
Project.
cycle, correct? Whole project.
Correct.
So now we little bit understood what the requirement is. Requirement is you have to lubricate automatically after number of wheels passed through that curve, right?
Correct.
So that way you don't need somebody to go and lubricate it manually, right?
Correct.
And also it's now connected to the cloud. They want the data, right? Whether it is a lubrication is fill, tank is fill or not, and other details they need, right?
Correct.
Okay, so now it is bit of a requirement is clear. Okay, this is the actual picture.
Of the equipment. Yeah, this is where the equipment, the device goes into. Correct.
Correct. Okay. So the pump, the tank, everything is on the side of it, right? This is the one, the pump and everything, correct?
Correct. The pump and the tank, the lubricant, motor pump,
Okay.
everything is inside this device.
Okay. So what are the outputs of this one? The 4 or 5 wires coming out, right?
So there are a couple of sensors. So you will see the wheel counter. Okay. So there's a proximity device that will count the wheels. Okay. So there's a train going on with a very large number of wheels. It will count 100, 150 wheels. So there's a proximity sensor coming in, and there's a lubricant going out. So that is the input here. Apart from that, you will have you on the box on this big unit that sits next to the rails.
Yeah.
Will have a lubrication tank and it's connected to the power. Okay, it's a 230 volts AC power is connected.
Okay.
And it has multiple other sensors that needs to send. For example, temperature data has to be sent, GPS data has to be sent, where it is, and the ID, location, and the other parameters are sent to the cloud. Yeah.
Okay. So this gives an overall idea.
Correct.
And this is the typical product which goes into the box, right?
Correct.
Okay, so I think this is the actual electronics we developed, right? So before going there on the architecture time, right? How did we choose what processor we have to go? So right now we have idea about our requirement, right? So it should have a sensor to count the wheels. It should have a control to control the lubrication pump, and then the cloud connectivity through GSM. And then there is a LED I can see. And these are all the requirements. So how did we decide on which microcontroller to go on the hardware side, the architecture? Now we are in the architecture phase, right?
So, okay, so that's a good point. Typically, customers come with the requirements. So they will give all these requirements, and also they will give the environmental conditions. So the environmental condition for this particular hardware, it's like you'll have to work at high temperature to low temperature. It's around 55 degrees centigrade to all the way to minus 20 degrees centigrade. So that's one environmental requirement. Other than that, it does also have to withstand extreme vibration. It is very close to the rails. So very close to the rails, you'll have a constant vibration whenever the rail passes on.
Yeah.
So it has to be a highly vibration resistant, temperature within the specified range, and they give the the inputs, like what type of sensor, what is the motor type, what is the pump type, and what are all the other sensors that they need.
Yeah.
And based on that, we take the number of inputs needed and the amount of processing needed, what are the types of IO needed. So you take, for in this case, we used a LCD. So LCD is interfaced through an I2C interface. We also have a Bluetooth device to calibrate, to do a UI. So we also added a Bluetooth through UART port. So there's a UART port to connect the processor to the Bluetooth. There is a GSM. GSM is also connected to one of the other UART ports. And it has to control multiple relays. So a general GPIO is good enough to control relays. There's an amplifier like a ULN 2000 or a transistor array to connect to get the relays driven from the microcontroller.
Okay.
And the other thing is the wide operating voltage, because it's on a remote location, you may not have a regulated voltage. So this device has to work from a wider operating voltage. So there's a large power supply here.
Yeah.
And interestingly, there are other things also need to be considered, because it is a field
Yeah.
input. Okay, field input, meaning you have sensors outside the box, right?
Yeah. Yeah.
So there can be lightning around it,
Mm.
or there can be high voltage sparks surges nearby,
Correct.
or there can be a radio communication, very strong radio communication nearby, or it can have a very strong uh, electromagnetic interference. So these
Mm.
are all the inputs we take, and
Correct.
we choose a controller that is suitable for this.
Correct. So the, the choice also is like industry grade and other grades you have to choose in the same controller also, right? Yeah.
Correct, correct. Some of them are auto qualified. In this case, that's an automotive grade actually. Even though it is railways, we choose an automotive grade.
Yeah.
So they are AEC 100, AEC 200
Mm.
grade components are used in this product.
Correct.
Correct.
So one thing is clear that making things work on the table is just a 10% of the work, right? The other thing which has to work as a production unit, that's where the expertise comes into picture, I guess, right?
Exactly, exactly. So it has to meet
Yeah.
all the compliance, compliance, particularly regulatory compliance as well as environmental conditions. Correct.
Yeah. Okay. So this one I can see a battery. So this particular design they ask for RTC as well, I think, correct? In this one?
Correct. So they needed an RTC to get the time, even though we have a GPS. If there's a shortage of GPS signal for some time or things like that, there will be a clock running, so the data can be communicated with clear details with
Okay.
the real-time clock. Correct.
Correct. So the RTC is here. I guess you're able to see the cursor. This
Yeah.
is the processor, and this is the SIM card for the GSM, right? And these are all the relays, right? Okay. Um, so once we choose while choosing the chip, we also have to think about the firmware side of it. Okay. So in this case, it has to handle parallelly how many threads you have to have in mind generally. Like there is a BLE and there is a GSM and there are other IOs, right? So we should not choose a chip which has more processing powers, because that's going to be unwanted cost as well as power ratings. So we have to choose a chip which is apt for the particular project. Um, so it also we have to also think about what are the interfaces we need. For example, this display is I2C interface, so the chip should have a I2C interface, and all other interfaces, whatever it is, we have to take care of it. This one, though it has BLE and GSM, I think we didn't go for any RTOS or anything in this case. I think we wrote the code in bare metal. That way, you just need a smaller footprint and smaller memory and flash. The another thing you have to consider in doing a product which is huge volume, we have to think about the cost as well. Um, uh, that typically comes in after the prototype and first development, but still we have to think, we have to design for a low cost. That's also has to be taken care. So now we kind of discuss the architecture phase. Okay. Once this architecture is done, then we'll move to the next phase. It will branch into two different phases actually. Okay. Let me show that phases, and then we'll discuss about our next phase on that. So you have the requirement here, and we discuss the software and the hardware architecture. Okay. So once the hardware architecture is done, then we'll move into the hardware design phase. The architecture document will be the input to the design. So hardware design, Sarana, what are the basic challenges you had in this project for hardware design, and what is the output of the hardware design?
So typically, this type of hardware, for example, they come out with the constraints. Okay.
Okay.
The constraints could be manufacturing related constraints. Um, so it has to be, for example, it has to meet all the compliance requirements. For example, it has to meet FCC regulations, or for India, so that's a BIS or a WPC regulation where we have a wireless device. So it has to fall within the regulatory requirements. And also, this has a high voltage is also involved here. You can see some slots on the next on this PCB. So it also have to withstand a higher voltage, and also should not have a shock or a leakage, electrical leakage. Right. So it has to meet the regulatory requirements or the safety regulations. And being an electronic product, it has also need to meet the ROHS standards, restriction of hazardous substances. So this is a primary information given, and so in this case, we had challenges with in the architecture. We need to have a high ESD EMI protection.
Correct.
You can see a lot of protection devices on the IO connectors. And there was a challenge in time to market where we need to develop it quickly because they need to deploy on the railways quickly. So, and there's a cost because it's going to be deployed across the country. It has to also come with a lower cost.
Correct. Yeah.
And being a railway system, right, it has to work for longer duration. So as per railways, if you take the railways itself, they would expect any product to work for 20 years. Okay. And they give support for 20 years. So you'll have to choose components and things that will be supplied for the next 20 years, typically. Okay. So in this case, being an advanced technology, so we got an exemption, and it has to be available for the next 10 years.
10 years. Okay.
So, for example, you choose a microcontroller, microprocessor. You need to ensure that the manufacturer will supply the processor for the next 10 years, because, and also there needs to be a higher reliability. This can be deployed in remote locations, inside forest, inside deserts, on a top of a hill somewhere, and people are not so easily accessible to go and repair it. Okay. So, and also while doing manufacturing, it has to be designed such that it can be tested easily. Okay. So these are all the constraints. So testing has to be done very fast. So we did a respin to do this, to get it doing a faster testing. So otherwise, if you do all the testing interfaces, it will take 3-4 hours to do a testing on each board. If you are making thousands of boards, we cannot spend 3-4 hours testing each board. So we'll have to be tested faster. So these are some of the constraints we get.
Okay.
And challenge. Yeah.
So with this one, we proceed with the schematics, right? That's where you the actual circuit is done, right?
Right. Taking into consideration everything, we start with the circuit diagram. We select the components. We do the circuit diagram. Maybe you can use that slide. The slide. Okay. There's a in the architecture side, we select the key components, the board dimensions, key components, type of interface needed. Then we go into schematics. We do the schematics entry. So first we need to do the symbols, then do a schematic entry, schematic review, followed by PCB layout design. Okay. So the schematics will pass on netlist to the PCB layout. The PCB design, the PCB designers will do the PCB and generate a Gerber files. Gerber files are sent to PCB fabricators. Okay, PCB fabricators and PCB assembly house. So there are 2 points. When you say PCB, it's a printed circuit board, the green color board you see typically, right?
Correct.
There is something called a PCB assembly. The
Yeah.
PCB assembly is with all the components mounted on it. Okay, so it has to be done in 2 factories.
Okay. So typically, what you pass, you just pass the Gerber files to them, right?
Uh, Correct. So not only Gerber files, there are drawings. Okay, there are fabrication drawings. There are PCB assembly files,
Okay.
or PCB, what we call it as a pick and place files. Okay.
Okay.
So for PCB fab house, or what we call as a fab house, we make the green color PCB, right?
Board. Just the
So
bare board, right?
bare
Without
PCB.
any components. Yeah.
Correct. Without any component is called PCB.
Yeah.
So that is manufactured with the help of Gerber files.
Gerber files. Correct.
Okay, so each and every layer will have a Gerber file. Okay, so there will be, if there are 4-layer PCB, there will be 4 electrical layers plus like a silk screen or the solder mask and other layers will be there.
Okay.
So that is sent to the PCB fab house.
Mm.
And components and component list and component XY location. Okay, so
Yes.
where is the component? So you need to find the XY location and send it to the PCB assembly house.
Correct. Yeah.
So once it is assembled, it is called PCBA or PCB assembly.
Correct.
So yeah, people generally confuse with PCB and PCBA.
PCBA, correct. Yeah. So with the components is PCBA and just the bare board is PCB, right?
Correct. Yeah.
So the assembly house themselves can get the components. You will specify exactly the part numbers, right? So for example, the same part, same microprocessor is available into multiple packages, right? With a different temperature rating and other things. So everything you will specify to the assembly house. They will buy and then they will bring it to you, right?
Correct. So it has to be very carefully decided. There are multiple packages for every part. For example, you take 741 IC, an op-amp IC, right? It comes with the surface mount, or it comes with through hole, or it comes with SO8 package, SO8 wide package. So you have to specify the part number, the manufacturer part number. So it's called MPN or manufacturer part number. So very, very important when you specify components on the bill of materials.
Okay.
The manufacturer part number is very important.
Yeah. Okay.
So yeah, maybe on the software side, you can also explain on what it takes to get to the software.
Yeah. So parallelly, when we completed the architecture, right, the software architecture is also decided. Like I just told you, like how many threads you're going to use. Are you going to use RTOS? RTOS is real-time OS, or just the bare C, embedded C are we going to use? In some cases, we might be using a stripped-down version of a Linux. Okay, that depends upon the application. Okay. Typically, in this case, we just used a bare C code, and then there it will be decided like how many threads we are going to use in this one, and what are all the interfaces we are going to use, and then we will design the software document will be come out of this design. So using this design document, developer will develop for every microcontroller. We'll have a development board, usually provided by the chip manufacturer. So because currently we are in this phase, right? Development phase. So till we don't have the PCB ready from our production, from our prototype PCB. So we'll be using the development board, and we'll develop the code and test it as much as possible. For in this case, for example, we would have bought the LCD and the development board and connected the LCD through a I2C connection, and then test the program. Okay. So by the time the PCB and the fab is on the assembly line, right, we would have had a unit tested code. Okay. Unit tested code here. Okay. So some of the this is the whole process. But we have to take care of whenever it is especially connected to cloud, we have to take care of the security. Normally we should use a secured connectivity between cloud and the device. Okay. We can use a secured connection. For example, it can be either HTTPS or MQTT, secured MQTT. We have to decide that in the software design phase itself. Okay. So the board will be tested and unit tested. Unit test report will be available, and this will be kept ready. Meanwhile, we'll have the board coming out of the fab and assembly. We'll have a PCBA in your hand. Then once it's done, there is a process called board bring up. Okay. This will be the exciting process where you have to power up the board first time. Okay. And there are again a lot of process. So actually we are giving a very, very high level. Each box itself, it has its own time. So for example, till now for this project, we would have crossed about probably like 2 to 2.5 months time by this time. Okay. So requirement would have gone for a week, architecture would have gone for another week or 10 days, and then design development would have taken you another 4 to 6 weeks time. Okay. So each and everything is a very detailed one. Every phase will have its own output document review and then checklists so that it goes to the next step. The board bring up it itself has a lot of steps. Like you should first physically verify if everything is correct, whether the components, the assembly house placed in the right direction, whether the pins are matching, do they have any soldered joints, any shorted joints, or any missed joints, any dry soldering. All these things you have to do. Okay. This is for prototyping. You have to do every component wise. It will be painstaking, but still you have to do. For this board, probably we'd have had around 200 plus components, right, Sarona, for this board, what we are talking, more than.
Yeah, it will be more than that, like
more
300 components.
300 components, yeah. So we have to take that. Then the sequence is powering up, right, Sarona? The each power section, you have to power it.
Correct. So typically it will start with power reset clock signals is what have been typically been tested. Each and every power, there can be multiple powers. So today, if you see, so good that you brought up that point. There are multiple voltages in a system. For example, there is at least 2 voltages for a microcontroller or a microprocessor. There will be a core voltage and there will be an IO voltage, and the IO voltage can be 3.3. The core voltage can be 2.5, 1.8, depending on controllers.
Yeah.
And there can be other devices. For example, you have a Bluetooth. The Bluetooth will operate at 3.6 volts. There can be relay. The relay operates at 12 volts, for example, in this case.
Yeah.
There will be an LCD that operates at 5 volts. Okay. So we need to have multiple voltages. And there's a special sensor. The wheel count sensor is a proximity sensor that needs 24 volts. Okay. So you'll see there are multiple voltage points. So we'll have to make sure that all the power supply is okay. Then once we get a reset, everything is okay. Then the software team takes care of it. Okay. And the next level of testing.
Correct. Yeah. And so once the powers is done, then everything is hardware team will make sure the powers are given at the right voltages given to all the components. Then the software team gets to it. When the designing board itself, there would have been a clear design how to program the board, like whether it's directly programmed through any programmer, JTAG or straight USB or through U-boot or whatever it is. We will have a plan for it, clear plan. Then the first time the board will be booted. the microcontroller will be booted with, and then one interface after another will be tested. Okay. For example, first the LCD that probably we already tested the development board will be now tested. Okay. And then the signal levels of each interface also will be tested at a hardware level. Okay, so just to see the clarity of the signal. Sometimes it might work, okay, on your table. If the signals are not clean, right, it may fail in the real world. Okay, so we have to make sure, though it is working functionality wise, we have to take care of that part. Then we'll make up each and every interface. After that, once all the interfaces are up, right, one after another, then we'll go for the application logic. Okay, the application is logic is it's what the customer needs. Okay, till now it is a technical need. So the application logic is what the customer needs. For example, in this case, right, the wheel counter will give you how many times the wheel counts. Okay, but there should be a logic. It says that after 500 wheels, apply more grease to it, more lubricant to it. Okay, so that part we have to write the code. That's the application part. And also we have a Bluetooth. In this case, we had a Bluetooth app. They can connect through the Bluetooth to this device and set the parameters. For example, today they want 500, tomorrow they want, after 1,000 wheels, they have to put, or the amount of lubricants to apply. All those things they can control in a Bluetooth app. Okay. And also for the GSM. GSM, it will send data about the status. Okay. What is the tank capacity currently, and then the number of times it applied, how many wheels it went, it crossed, or number of trains it crossed. Those has to be written. So all these things will be tested in DVT. Okay. So DVT is design validation testing. Okay. So in the requirement, you would have done some probably over 100 line items. Okay. For example, I also forgot to mention about there are keypads in this one, right? The IOs, you'll directly use the IOs for the key. As soon as you press, there should be a menu there in the LCD. The requirement they would have mentioned, when the user presses up arrow, what has to happen? Okay. When he presses enter, what has to happen? So those things, the functional verification will be done in the DVT. Okay, so that will be an exhaustive task. Depending upon the project, it will take it one time. This is DVT. Okay, once this is done, right, at this point, we can give the board to the customer to test from their end. Okay. At this point, we didn't test about any other requirements, constraint requirements, like Sarona mentioned about the temperature and other things. Okay, so those things are taken care in EVT, right, Sarona? After that, okay. So the next things
Yeah.
will be.
Yeah. Sorry.
Okay, I thought I missed you. Okay.
Okay, not a problem. Okay, so the EVT DVT is mixed up here. Okay, that's fine. So before there's a functional verification done, then there is a validation on the design specs. So not only just functionality, right? So when there's a clock, you need to check the clock timing. When there's for example, if you have a I2C signal, you need to see clock with the data line, timings we need to check, setup time, hold time,
Yeah.
and also power margins. Okay, so when you have a 3.3 volts logic, for example, so there's a microcontroller operates at 3.3. So you cannot expect all the power supply to give exactly 3.3 volts, right? So there can be a margin of 3.4 volts, or it can go to 3.2 volts. Okay, so we'll have to ensure that the device or the entire design works from 3.2 to 3.4, for example. Okay, if it's a 5-volt device, we'll have to test it from 4.5 or 4.75 to 5.25 volts. So, for example, that's the DVT part. Then you go into production validation testing, which means you will have to ensure that you make, say, 20 units or 100 units. The 100 units is manufacturable, right? So you cannot have yield problem. Like you make 100 boards and you get 10 boards failure, like solder joints problem or assembly problem, or it takes too much time for assembly, or how do you test it? So all these things are validated in the production validation testing. So typically it will go like three phases before hitting production. Okay. So on some projects it can start to end. It can be like 6 months. Some projects it can be easily 1 year to 2 years, depending on the type of projects.
Yeah. So this one, I think typically it went for about 6 months, I guess, right? For us.
Correct. Yeah, it went 6 months. Yeah.
Okay. So, so that's a overall high level. I think we brushed it up, but still, this should give a idea of what's happening behind the screen. I think one thing we didn't touch here is the enclosure for it. Okay, not for this one itself, but for any electronic product, industrial design, right? Enclosure. That's also a major component. Correct.
Correct. So industrial design. So first you need to look at the ergonomics plus usage, and also it has to meet certain specifications like IP. IP is ingress protection. Okay. So ingress protection meaning dust should not go inside, or water should not go inside. There are different category of products. Okay. So mobile phones, you will see these days advertisement as IP65. Okay. So it can have light water spillover on it, and dust will not go inside. A big dust will not go inside. That's IP rate. One for IP 6 and 6 or 5. The first digit is for water. The second digit is for dust rating. Dust and water. Okay, so typically you will see on a mobile phones, you will see IP65 or something like that.
Yeah.
So, and on top of it, it also have to withstand the vibration, temperature rating, and also usable. Okay. This product actually goes inside the rail system. So the aesthetics importance was not given that much, but still from the other user point of it, UI point of it, that there was a lot of importance given so that the user can easily use it, right? So you will have minimal buttons and a simple display.
Correct. Yeah.
Yeah, that's
they have been using it for long now, so they are very comfortable with this one. I think. Yeah.
Correct.
So different projects needs different industrial design. So somehow, if it is a consumer product which comes to the end customer, end consumer, then it lot more care has to be taken for the look and feel of the device, durability, and then there will be a drop test. All of these things are there actually. So there are much more than we covered now. Yeah. Let me also go to the another product. So the pictures you see is the one whatever we did it, and then inside the box on the PCBs. Let me go to the next product. Okay. This is a ultra low power BLE mouse. Okay. This one we designed here. Designed and developed here the prototypes, and then we manufactured around 100 units and we gave to the customer. So this product, if you see, it's a BLE mouse, Bluetooth low energy mouse. It is ultra low power. Okay, that means this chip company manufactures very low power BLE chip. It just takes 10% of the normal BLE chips. So that means if a BLE chips comes for with a AA battery comes for 6 months, then this one comes for more than 2 years time. Okay. Um, so this also had the same uh, architecture phase, then the design phase, and the PCB layout, schematics, PCB layout, and fab and assembly, software programming, okay, firmware programming, and testing. Okay, so in this one, we'll see what are all the some challenges we made to come up with. Okay. Um, uh, I don't know how many of you are actually the nowadays all the mouse works as a it has a very small 24-bit camera inside the sensor. So it takes a picture of your surface, and as soon as you move, it will again take another picture, and it will compare the previous picture and this picture, the pixels, and then it will find out which direction you moved. Okay, that's what this sensor does. Okay, the sensor,
I'll add one more point here.
yeah,
This is like a 19 or 20 pixel into 20 pixel camera. So
correct,
any mouse you will see today, there's an optical mouse, right? So the optical mouse is basically a camera and has a DSP inside. You can see a small light, a blue color light or a red color light, and a small lens for the camera. It's a small, tiny camera,
yeah,
20 across 20 pixels. Okay, monochrome. It takes pictures of the surface, as you said.
correct.
Careful alignment is needed. So while manufacturing, there is a lot of challenges. You need to have a clean level to get the correct pictures.
Correct. Yeah.
Yeah, go
Yeah.
ahead.
Yeah. So, unless the other product, right? This is a different domain because this operates in battery. Okay. Any electronic device which operates in battery and which operates in power, the design is totally different. Okay. So the power side, we don't need to worry about the battery life, how long it has to work. But any battery operated device, we have to think power saving from hardware till software. Okay, till software and the delivery. Um, so we have to choose parts which is consumes less power. For example, this sensor is there, right? This sensor, if you choose for a wired mouse, probably we can choose any sensor because we don't need to worry about the power. But since it's a battery operated one, it's a wireless one, we have to choose a part which consumes very less power. Okay, this will be in microamps. Okay, so from that point it starts the architectural part. The more less power sensor we go, more difficult to work with because the one I shown is a little bit bigger, but there are very small, like the sensors will be the size of 1 mm into 2 mm, and that has to be used in the boards. Okay. Actually, curious people can open your old mouse and see what things are there under your mouse. Um, so that's one thing, that the sensor gives the cursor movement, and there will be a wheel which with the tracking wheel, and then the tracking wheel button and the left and right mouse. So these are the hardware things, and this will be operated by a 3 volt, and like Sarana mentioned, there will be a power section in this as well. There will be the main controller, that's a Bluetooth BLE controller. The BLE chip itself has a controller within it. It will have a processor core, so we can use that core to do the processing itself. So you don't need a separate processor for BLE and your normal processing. Okay, and there will be a antenna. This is a onboard antenna. Okay. Uh, uh, so this is the overall hardware design of it. Okay. So when you come to the software part of it, okay, so this is a mouse. So it has to work with all the PCs in the world. Okay. Uh, Thankfully, the protocols are there. So if you just write a code for that HID protocol, it's Human Interface Devices protocol is there. If you write code for that, 80-90% of the devices should work. Okay, but still there will be a lot of challenges. Okay, so it might work in one version of Windows, other version may not work, based on a lot of other issues. The timing of the changes we send, and we'll get a lot of issues in there. But we have to overcome all of those things in the testing. Okay. And then sticking with the HID protocol as per the SID protocol documentation. Okay, so on the software side, since it's a battery
Yes,
operated.
we need to. They are waiting for questions.
Oh,
So
okay. Yeah, I think we are. I think they got the picture now. I think.
okay.
So we can take questions. Oh, it's already time. Yeah. Um, are you seeing the questions in your screen, Sarana? We can go one by one.
Let me see the questions. Chat.
You can
Yes.
ask if you want to. Okay,
Go
sir.
ahead
So
with
the
the questions.
yes, sir. So the first question we have is that, so other than GSM, what can be used for communication in this system?
Yeah, we can use any communication. So GSM is just one. In this case, we used a 2G one, like a GPRS communication. But you can use LTE, or there are long range communications like LoRa, um, and also you have a Sigfox is there. LoRa is becoming popular. It's all depending upon the situation you need, like the requirement. Okay, in case if there is no network connectivity, right, then we can use LoRa. And these cases, you don't need to put a LTE or 4G, okay, because this is not a high bandwidth, right? Like you just have to send few data every few hours. So we just went for 2G. And also there are new technology coming up in NB-IoT is there. We can use that. So there are a lot of communication methods. So it depends upon, we can use any of them.
Yes, sir. Thank you, sir. That was very informative.
Yeah.
So the next question we have is that consumers expect a certain year of durability from these products. So how do you make sure that it is achieved, and how can you claim that a product will last for 20 years?
Okay. Quite interesting question. So, product lasting for 20 years, we'll have to do a halt testing. So it's called the highly accelerated life testing. Um, so, for example, if you want to have a life cycle of 20 years, so there can be so all the parts come with the MTBF data, a mean time between failures. Okay, so that is for so you can do a math to find out the probability of failures of each component. Okay, and do a reliability calculation. Okay, so typically people enter the MTBF data and take a probability of all the components and arrive at a reliability value. Okay, so that is one part. And the life part, okay, the life of the device itself should be, say, for example, in this case, it should be rated for 20 years. So in this case, it is rated for 10 years. So other application like aerospace, like a commercial airlines or real trains, hardware that goes into train system, that has to work for 20 years at least. That may be the requirement. Okay, and that is also the standard as well. So there is a test called HALT testing. Okay, highly accelerated life testing. So typically people do a temperature cycling. Okay, so for example, there will be temperature cycles over a period of time. So the temperature is cycled between minus 20 degrees to plus 50 degrees every half an hour. They keep cycling for a few months to find out how long, what is the temperature cycle it can withstand, and also vibration and other tests they can be done. Temperature, voltage, frequency, all these, there's a cube test, we call it. The cube test can be done for high reliability products. So this is not a high critical, high reliability product. Failure to function will not result in a safety hazard. Okay, so if at all, if there's a lubrication does not happen one time or two times, there's nothing is going to happen. Only the wear and tear will be more. So it's not going to be, safety is not compromised. So on the other hand, there can be a critical device, class 3 device we call it as, where failure to function will result in an accident or a death of one or many people. Okay, so or injury, human injury. So they are called safety critical devices, where reliability and other things are extremely important. Yeah, that's about it in this case. Yeah.
Yes, sir. Thank you, sir. You have explained it so well, and I hope everyone understood it. Um, Now we have come to the end of the session. We would like to thank Mr. Sarvana Perumal as well as Mr. Sarvanan Pavan for taking out this time to enlighten all of us. Thank you so much, sir, for having you today.
Thank you very much. Thanks for hosting us.
Thank you, sir.
Thank you. Bye bye.
This session is a part of AccessDenied' 2021. The 3 days of AccessDenied' 2021 is nearing the end, and we have the much awaited valedictory ceremony and the prize distribution ceremony at 8 p.m. tonight. Do join